Episode 68, titled Synthetic Data, Why It's Used, How It's Sampled, and Where It Misleads, the goal is to understand synthetic data benefits and dangers for exam scenarios, because synthetic data is often presented as a solution to privacy and scarcity problems, but can quietly introduce new risks. The exam cares because questions about synthetic data usually test judgment, when it is appropriate, what it can and cannot prove, and how to validate that it is not misleading. In real systems, synthetic data can help teams collaborate without exposing sensitive records, and it can help address class imbalance by augmenting rare examples, but it can also create a false sense of confidence if the generated data fails to reflect the true complexity of the environment. Synthetic data is not fake, so it does not matter, and it is not safe, so it solves privacy automatically. It is a tool with specific strengths and failure modes. If you learn those failure modes, you can use synthetic data to support decisions rather than distort them. The core discipline is to treat synthetic data as a proxy that must be validated against real behavior, not as a replacement for reality. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series.
Synthetic data is generated records that resemble real distributions, meaning it is not a simple anonymization of existing records, but a constructed dataset meant to preserve patterns without exposing exact individuals. The generator can be a statistical model, a machine learning model, or a rule-based simulator, but the goal is to produce data that looks plausible and that captures key properties of the real dataset. This resemblance is always partial because the generator must choose what to preserve, such as marginal distributions, joint relationships, or temporal dynamics, and what to smooth away. The exam expects you to recognize that synthetic data quality depends on what properties it preserves and how faithfully it preserves them, not on how realistic it looks at a glance. Synthetic data can also reflect the biases and limitations of the real data it was derived from, because it is generated from learned patterns or specified rules that come from that original source. When you define synthetic data clearly, you emphasize that it is a generated approximation of a real distribution, not a guarantee of truth. One of the most common uses is privacy protection, because synthetic data can allow sharing and development without exposing raw, sensitive records. Teams can use synthetic datasets to prototype pipelines, test data schemas, validate integration logic, and perform exploratory analysis in environments where real data cannot be moved or widely accessed. Synthetic data can also help when you need to share examples with partners or auditors, but cannot disclose actual personal information, although the safety of that sharing depends on how the synthetic data was generated and what risk controls are in place. Another common use is expanding rare class examples, such as generating additional positive cases for rare events, which can help models learn patterns when true positives are scarce. The exam often frames this as data augmentation, and it expects you to recognize that augmentation can improve learning, but also can distort calibration if synthetic positives do not match real positives. In practice, these uses can be valuable, but only when synthetic data is treated as a supporting resource rather than as a substitute for real evaluation. When you narrate these motivations, you show that synthetic data is used to reduce constraints, not to eliminate the need for real-world validation. Sampling methods vary because synthetic data depends on the model or rules used to generate it, and understanding that dependency is key to judging what the synthetic data can preserve. A rule-based generator might sample from specified distributions and constraints, producing data that matches designed marginals but may miss complex interactions. A learned generator might sample from a model trained on real data, producing more realistic joint patterns, but potentially reproducing bias or memorizing rare, sensitive patterns if not controlled. Some approaches generate each record independently, while others attempt to model sequences, correlations, and conditional relationships, which matters when time ordering and interactions drive outcomes. The exam expects you to recognize that generation is not just random noise, it is structured sampling from a learned or specified process, so the quality of that process determines the quality of the data. Sampling also involves choices about how to handle rare events, missingness, and constraints, and those choices determine whether the synthetic data represents tails and anomalies accurately. When you connect sampling to the generator, you demonstrate that synthetic data is only as good as the assumptions built into the generation mechanism. Mode collapse is one of the most important failure modes to watch for because it creates synthetic data that looks plausible but lacks diversity and rare behaviors. Mode collapse means the generator produces a narrow set of common patterns repeatedly while failing to produce less common but important patterns, often because those patterns are harder to learn or are underrepresented. The result is a dataset that matches the center of the distribution but underrepresents tails, edge cases, and unusual combinations that can be critical in security, fraud, and operational reliability. This can make a model trained with synthetic augmentation look better in development while performing worse in the real world because the model has not been exposed to the full diversity of reality. The exam may describe synthetic data that looks too clean or fails to include rare outcomes, and the correct reasoning is to suspect missing diversity. Mode collapse is especially dangerous because it can go unnoticed if you only validate simple summary statistics that focus on averages rather than on tails and interactions. When you narrate mode collapse, you are warning that synthetic data can be deceptively smooth and incomplete. Validating synthetic quality requires comparing key distributions and relationships, not just checking that values fall within reasonable ranges. A strong validation compares marginal distributions of important features, joint distributions of pairs or key combinations, and relationships between predictors and outcomes, because those relationships determine whether models learn the right patterns. You also want to compare tail behavior, such as percentiles, rare category frequencies, and extreme value patterns, because synthetic data often fails there first. If the synthetic data is intended to support time-based decisions, you also need to compare temporal patterns like seasonality, autocorrelation, and event sequences, because independent sampling can destroy time structure. The exam expects you to use validation as an evidence-based check, not as a cosmetic assurance, because synthetic data can look realistic while still being wrong in ways that matter. Validation should be framed as, does it preserve what we need, rather than does it look real, because looking real is not a reliable quality test. When you validate systematically, you treat synthetic data as a model output that must be tested, not as a gift. Training only on synthetic data is risky because synthetic datasets can drift from reality, smoothing away complexity and amplifying biases that exist in the generation process. Even if synthetic data is derived from real data, the generator may miss rare events, distort correlations, or fail to represent new patterns that emerge after the generator was trained. A model trained solely on synthetic data may learn artifacts of the synthetic generation process rather than the real-world process you care about, leading to poor generalization. The exam expects you to recognize that synthetic can support development, testing, and augmentation, but real-world evaluation and calibration still require real data. A common safe pattern is to use synthetic data to augment training or to test pipelines while keeping evaluation anchored on real data, because evaluation is where you must measure true performance.
Synthetic-only training can be useful for stress testing and simulation scenarios, but it should not be treated as evidence that the model will perform in real deployment.
When you narrate this caution, you emphasize that synthetic data is a proxy, and proxies must be anchored to reality. Legal and ethical implications matter because synthetic data can still leak patterns, especially when it is generated from sensitive populations, or when the generator memorizes or reproduces rare identifiable combinations. Synthetic data can reduce direct exposure of individual records, but it does not automatically eliminate privacy risk because generated records can still reflect sensitive attributes and correlations that enable re-identification when combined with external information.
Licensing and consent constraints may still apply if the original data had restrictions on derived use, and governance frameworks may treat synthetic data as regulated if it can be linked back to individuals or if it reveals sensitive group-level patterns.
The exam expects you to recognize this nuance. Synthetic is not a blanket exemption from privacy, and you must still assess whether sharing and usage are permissible and safe. Ethical issues also arise when synthetic data replicates biases and then amplifies them through training, creating a model that reinforces inequities while appearing safe because the data is synthetic. When you communicate these concerns, you are showing that synthetic data sits at the intersection of technical and governance risk.
Scenario practice is important because the safest use of synthetic data depends on whether you are testing, augmenting, or sharing, and each scenario has different success criteria.
For testing, synthetic data can validate that pipelines handle schemas, edge cases, missingness, and scaling without exposing real data, and the goal is functional correctness rather than statistical fidelity.
For augmentation, synthetic data can increase representation of rare classes, but it must be validated to ensure it does not distort the class boundary or calibration, and it should be combined with real data rather than replacing it. For sharing, synthetic data can enable collaboration, but it must be assessed for privacy leakage and licensing compliance, and it should preserve only the level of detail necessary for the intended purpose. The exam often frames these as separate options, and the correct choice depends on the constraints and goals stated in the scenario.
When you practice these distinctions, you show that you can choose synthetic data use cases that reduce risk rather than introduce new risk.
A disciplined answer always ties synthetic usage to purpose and validation.
Synthetic data can affect calibration and real-world error rates in ways that look subtle but matter operationally. If synthetic augmentation changes the distribution of features or the prevalence of the target, a model may learn probability estimates that do not match real-world frequencies, leading to poorly calibrated scores. This can increase false positives or false negatives at operational thresholds, even if ranking performance appears improved. Synthetic data can also shift error patterns across segments if the generator underrepresents certain populations or rare combinations, causing unequal performance and fairness concerns. The exam expects you to monitor these effects by evaluating calibration and error rates on real data, not just by looking at overall accuracy improvements during training. Monitoring also matters after deployment, because if real data changes and the synthetic generator does not, the gap between synthetic and real can widen. When you narrate calibration risk, you show that you understand synthetic data can change not just performance, but the meaning of probability outputs. Documentation of the generation method and limitations is essential for governance and audits because synthetic data is a derived artifact with assumptions that must be transparent. Documentation should include what generator was used, what input data and time period it was trained on, what features and relationships it was designed to preserve, and what privacy protections or constraints were applied. It should also include known limitations such as underrepresentation of certain tails, reduced diversity, or lack of temporal structure so users do not misuse synthetic data for conclusions it cannot support. The exam treats this as responsible practice because synthetic data is easy to misapply when its creation process is not understood. Documentation also supports reproducibility because regenerated synthetic datasets can differ across versions if the generator or input data changes, and version control helps track those changes. When you document synthetic data properly, you reduce the risk that it becomes an untrusted black box.
Communicating results derived from synthetic data requires disciplined language because synthetic data should support analysis, not be treated as definitive ground truth.
If you used synthetic data to test a pipeline, you should say it validated functional logic, not that it proved performance in the real world.
If you used synthetic data to augment training, you should present performance results based on real evaluation sets and describe synthetic as a training aid, not as evidence.
If you used synthetic data for sharing, you should clarify that conclusions drawn from it are limited to the properties that were validated and preserved, and that certain fine-grained or tail behaviors may not be represented.
The exam expects you to match claim strength to evidence source, and synthetic data is inherently one step removed from reality. Communicating this clearly protects stakeholders from overconfidence and protects you from accountability issues when synthetic-based assumptions fail.
When you describe synthetic results responsibly, you are maintaining trust by being explicit about what synthetic supports and what it cannot guarantee.
A helpful anchor memory is, synthetic helps scale safely, but can distort truth.
Scaling safely refers to the ability to develop, test, and collaborate without exposing raw, sensitive data, and to increase representation of rare classes when real examples are limited.
Distorting truth refers to the risk that synthetic data smooths away diversity, misrepresents relationships, or encodes generator artifacts that do not match the real-world process.
This anchor helps on the exam because it prompts a balanced answer. Synthetic is valuable, but it must be validated and bounded by cautious interpretation.
It also reminds you that the safest synthetic use cases are those where functional testing and privacy preservation are the goal, while the riskiest use cases are those where synthetic is treated as a substitute for real-world evidence.
When you apply this anchor, you naturally include validation, governance, and real data evaluation as part of any synthetic plan. To conclude episode 68, choose one safe synthetic use and one red flag, because this demonstrates both appropriate application and risk recognition.
A safe use is generating synthetic records to test data pipelines, schema changes, and integration logic, ensuring systems handle missingness patterns, edge case values, and scaling without exposing sensitive production records.
This is safe because the goal is functional correctness, not statistical proof, and any model performance claims can still be evaluated on real data later.
A red flag is using synthetic data as the only training and evaluation dataset for a deployed model, because synthetic can drift from reality, underrepresent rare behaviors, and distort calibration, producing a model that looks good on synthetic benchmarks, but fails under real conditions.
If you see that red flag, the corrective posture is to anchor evaluation on real data and treat synthetic as augmentation or testing support rather than as ground truth. This is the exam-ready judgment. Synthetic data is useful, but only when you respect its limits and validate that it preserves what you need without pretending it replaces reality. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.